Alright, so this section is basically application problems where you're going to try to optimize a function, and by optimize we mean maximize or minimize. So find perhaps the most economic option. So the first problem is a little example where you are going to have to build a box. So you're going to try to design a box that is going to be made out of a piece of cardboard, 36 by 36 inches, and you're going to cut out squares, and you're going to then bend the sides that are going to be left. So bend it right through the, well, that should be straight lines, and then you're going to tape the seams, and you're going to obtain a box, little box to contain a certain volume. What we want to do is maximize that volume. So what is going to be our strategy? Normally, these problems will have a constraint and a target function. The target function you will identify because the problem will tell you maximize something or minimize something. So in this particular case, our target will be to maximize the volume. So that means we will have to write the volume. Let me write it like the whole word. We will have to maximize or find a function for the volume. And to do that, we're going to use the next thing that is going to be given in the problem, that is going to be a constraint. So in this case, the constraint is given by the size of the cardboard piece. So it's usually, when you read the problem, you're gonna find there's going to be a limiting factor. And in this case is that we have a piece of cardboard that is 36 by 36. We cannot come up with more cardboard, so that's going to impose a constraint. So that one is usually the one that takes a little bit more work to write in equation form. So let's start with that one. So at the moment, I have no variables. So let's set some variables. Let's say that the side in here is y. Let's identify that side up in our picture above. That side would correspond to this side right here. So then I have, since the piece of cardboard is square and I'm going to be cutting square cutouts, I know that this side is also going to be of size y, because the original piece of cardboard is square and I'm taking out square cutouts. So that is given. So now the height is obviously not going to be the same. So let me call that x. I'm going to make a little arrow here because I cannot fit it in there. So let's call the height x. Let's identify where x is in our picture. Well, x is the size, man, I can barely fit it. It's going to be the size of the cutout. That's going to be x. So the constraint is given by, you can read it off of this picture because you have that x plus y plus x must be equal to the side of the cardboard piece, which is 36. So x plus y plus x must be equal to 36. Because I'm making my cutouts from a 36 square inch, 36 squared square inch piece of cardboard. So in this case, I get that 2x is going to plus y is going to be equal to 36, and then I can subtract from there 2x on both sides and get 36 minus 2x. And this constraint, I'll box it even though it's not an answer, but just because it's going to be important to us, because we're going to use that to write our target function in terms of a single variable. So we're going to usually, this is not always the case, but usually we'll be able to write a target function, but usually it will involve two variables. So we'll use our constraint to turn it into a single variable problem so we can take our derivatives as we know. At the end of the course, we will do some problems where we're going to actually have multiple variables, but this is we're starting, so this is going to be in one single variable. So let's try to write the volume then, the target function. So the volume of this box, just talking about the two, with the two variables. Well, what is the volume of a box would be the base times the height, so y times x, times the depth, which is y again. So you're going to have y times x, which is going to be y squared x. And that is going to be 36, substituting my constraint, my equation from the constraint into the target. So it's going to be 36 minus 2x. I'm substituting in for y, and y appears squared, so I square that term, and then times x. So all I did was plug in into my volume formula. I'm plugging in my constraint. So now I have a target function, and the option is that it's a function of a single variable. So I can apply what we did in the previous sections and find the maximum. Now, if you remember, absolute min and absolute max are a lot easier. And these physical problems actually we're trying to find the maxima and minima on a closed interval. So that is an advantage. Let's find what interval that is for this function. Well, what is the minimal size of x that you could choose? Well, you cannot choose negative x's to start with, so you can choose only numbers greater than 0. And what would 0 correspond to? Well, 0 corresponds to the box that you form, which is really not a box, it's just a piece of cardboard that when you don't cut anything out. So the box would have no height, so the volume would be 0. And you can check that if you plug 0 into this equation here, you're going to get 0, because you have 0 times 36 squared, 0 times anything. It's going to be 0, so you have that. And now what is the other cutout you could make that would make this box inexistent? Well, that is if you cut right through the middle, because that would give you 4 pieces of cardboard. So you make x a half of the length, and that would give you 4 pieces of cardboard but no box. So that would be whenever x, which remember x is just the size of the cutouts, is going to be 18. So when you do half of the length. So those would be our options. Let me erase those lines because they're not part of the problem. So that would be your closed interval. That would be where you're looking for the max. So what do we do when we want to find a maximum or minimum on a closed interval? What we do is we set the derivative equal to 0 and solve, and then we evaluate the function on the endpoints and on the critical numbers, and then we check which one is the maximum and which one is the minimum. I did not say we find when the derivative is undefined, only because this is again a polynomial, so it's always defined. If it would be a rational function, then I do have to be careful with that, or if it's any other kind of function, I have to be careful with that. But in this particular case, it's just find the derivative, set it equal to 0. So let's do that. So to find the derivative, I have a product, so I have to do product rule. So I take the derivative of the first, which is you lower the exponent, copy the inside, then raise it to the power of 2 minus 1, so just a power rule. But then you don't have x inside, you have 36 minus 2x, so the chain rule tells you have to multiply times the derivative of the inside. Derivative of the inside in this case is negative 2. You still have to multiply, so that's this whole thing is derivative of the first. You still have to multiply times the second. So derivative of the first right here times the second plus copy the first, 36 minus 2x squared, and times the derivative of the second, which is 1. So that's it. Well, we set this equal to 0. And what do we do? Well, we have to notice that we have a 36 minus 2x common factor. So whenever we're solving an equation equal to 0, it's very convenient to factor things out, because then we already get one root for free. So we can do that. We factor this 36 minus 2x, And then here, what am I left with? I'm left with a 2 times negative 2 times x. So negative 4 times x. That is just 2 times negative 2. 2 times negative 2 times x. And then plus, when you factor one of these two guys, you're left with another one. So 36 minus 2x, you just copy it. And what do we get? Well, we get 0 equals 36 minus 2x equals, or sorry, times 36 minus 6x. And we have two factors that multiply out to 0, so this can only happen if each term becomes 0 at a certain point. So if you set the first one equal to 0 and you solve, you obtain that x is going to be 18. Just add 2x on both sides and divide by 2. Or if you set the second term equal to 0, you obtain that x is equal to 6. Notice that x equals 18 was an endpoint already, and so we have to evaluate our function, our volume function, at both endpoints and at the critical value we found right here. So we evaluate it and we obtain what? Well, for x equals 0, you have 0 times something, that's 0. And for x equals 18, that would be 36 minus 18 times 2, which is 36. So it gives you 0. So 0 times 18, that's still 0. Here we would have 36 minus 12, that's going to be 24 squared times 6. So this, let me calculate it real quick. So I get that. Certainly this is a minimum, absolute minimum. This is a minimum, and this is a max. Absolute, all of them are absolute, mean absolute max. So what are the dimensions that maximize the volume? Well, the box, the resulting box would be, let's draw it here. The height would be 6. Y would be 36 minus 12, which is 24. Beautiful box, by the way. And then this is 24. And those are dimensions of the box that maximizes the volume. So this volume would be equal to 3,456 square inches. And so that's that. So these problems, the trick is always to just try to find your target function, try to find your constraint, write them in a mathematical way, set up your equation, then you take a derivative, and before you find your derivative, you find your domain, then you find your derivative, and you then determine whether you have where you have minima and maxima. And that's it. All right, guys. Sorry that this video went a little longer. The problem was a little more involved, so in any case, that is the answer. If you have any questions, just let me know. Thank you.